You have learned that materials are classified as conductors, semiconductors, and insulators based on their electrical conductivity, which in turn depends on their atomic structure. For example, copper is a conductor, silicon is a semiconductor, and wood is an insulator. A silicon crystal. We know that in a crystal, there is a regular arrangement of atoms with constant interplanar spacing between them. The electronic configuration of silicon is 1s2, 2s2, 2p6, 3s2, 3p2. The third orbit, with 4 electrons, is the outermost orbit. Hence, silicon has valency equal to 4. As silicon has a crystalline structure, there are interactions between the neighboring atoms. Let us assume that there are n silicon atoms in the crystal, each with 4 valence electrons. For silicon, in the outermost orbit, there are 8 energy states available, out of which 2 states belong to 3s orbital and 6 states belong to the 3p orbital. Therefore, for n atoms, the total number of energy states available in the outermost orbit is equal to 8n. At the distance between the atoms observed in crystals, such as silicon, these 8n energy states split into 2 levels, each having 4n energy states, due to the atomic interactions discussed earlier. In a crystal, each energy level or state is split up into a large number of closely spaced sub-levels. A group of such sub-levels with continuous energy variation is called an energy band. For a silicon atom, the lower 4n energy states contain electrons that are in bonding, and such energy states are called the valence band. Therefore, the term valence band refers to a group of energy levels which contains bonded electrons. We know that the electrical conduction in solids takes place by virtue of electrons, which are free to move, that is, by means of free electrons. Since the electrons in the valence band are bonded, they do not contribute to the electrical conductivity of a material. The higher 4n energy states contains those electrons which are free to move about, and as such, they contribute to the electrical conductivity of the semiconducting material. The group of energy levels occupied by such electrons that helps in conduction is called the conduction band. Let EC denote the lowest energy level of the conduction band. Let EV denote the highest energy level of the valence band. The difference between EC and the EV is the energy band gap or energy gap denoted as EG. The valence band electrons can move into the conduction band by gaining energy equal to the energy band gap EG. Thus, there exists a band gap between the lower valence band energy levels and higher conduction band energy levels. For a silicon atom, this energy gap Eg is about 1.1 electron volt. This means that for a valence band electron to move in the conduction band, it needs a minimum energy of 1.1 electron volt. At room temperature, we find that a few electrons of the valence band gain thermal energy equal to the energy band gap to move into the conduction band, and hence become free electrons. The vacant energy levels in the valence band create the opportunity of other valence band electrons to move into them. Therefore, in such solids, conduction is possible due to the conduction band electrons, as well as due to the vacancies in the valence band. This is the reason why a semiconductor displays higher conductivity at higher temperatures. However, as the temperature decreases, we find that there are fewer electrons in the conduction band than at higher temperatures, and hence conductivity decreases. At the temperature of 0 Kelvin, the conduction band is practically devoid of any electrons, and as such, there cannot be conduction possible through the semiconductor. Hence, at 0 Kelvin, a semiconductor behaves as an insulator. This is the case of the semiconductor crystal. It is important to note that the band gap is different for different solids. Let us now look at the specific case of solids where the energy band gap Eg between the conduction band and valence band is very small, or the conduction band overlaps the valence band. When such an overlap occurs, the band gap Eg is nearly zero. In solids where a very small band gap exists, with no external energy available, there are no electrons in the conduction band. When a small energy is supplied, the valence band electrons move into the conduction band. Now let us look at the situation where the conduction band overlaps with the valence band. In this case, the valence band electrons are available to move into the conduction band and thus are readily available for conduction, which happens in the case of metals. Since a large number of electrons are available for conduction, the electrical conductivity is very high for such solids. We know that solids having very high electrical conductivity are called conductors. For some solid, there exists a very large energy band gap greater than 3 electron volt. In such solids, it is practically impossible for the valence band electrons to move into the conduction band, since the energy required is very high as the band gap is very large. Such materials then have very few conduction electrons, and hence have very low electrical conductivity. Such materials are characterized as insulators. In semiconductors, we have seen that a finite but a small band gap of less than 3 electron volt exists, and as such, by supplying sufficient energy, the valence band electrons can move into the conduction band. Therefore, the semiconductors have conductivities between that of the conductors and insulators. Thus, we see that on the basis of energy bands, materials can be classified as conductors, semiconductors, and insulators, with conductors having a very small or nearly zero band gap, semiconductors having a finite and small band gap of less than 3 electron volt, and insulators having a band gap of greater than 3 electron volt.
दोस्तों, यदि आज की वीडियो आपको अच्छी लगी हो तो लाइक कीजिए, चैनल को सब्सक्राइब कीजिए और अपने दोस्तों के पास इस वीडियो को शेयर कीजिए। अगर आपका कोई कमेंट हो तो कमेंट बॉक्स में नीचे जरूर लिखिए। थैंक यू।